Hey there, it is Miss Safford from the future. I want to just start this video by saying it's a little bit choppy, and my apologies, but this is a review video for the covalent compounds and covalent bonding test. So the first part of the test review, you're just going to see a lot of notes. So you're going to see the video get a little choppy here in a second, but I'm going to start talking in just a minute about some of the things that you're going to want to know. You have this already in your packet. So that is where this video is going to begin, just going over the review topics. We did on covalent. Y'all did great on that. Review these shapes. And don't forget, ionic bonds transfer, so they do that swap and drop. While covalent bonds, what you see is what you get. So if you see a prefix, that means it's covalent. So what you see is what you get. Okay? Compare that to if we see Roman numerals. This is an ionic name. So this one we have to crisscross. So cobalt 3 sulfide. Sulfur has a -2 charge. The 3 over here, they crisscross. Okay, so that's a weird looking 3, but that is a 3. Review your acid naming. Okay, if you see a hydro, that means it's a binary acid. Hydrofluoric acid, that's just going to be HF. Yes. That is different than if you don't see the hydro. It's not. I'm not just going to write HP. That's not correct. It's OUS. Okay, so I see that ending OUS, so I'm thinking dynamite, ITE, is dangerous. That means it was originally phosphite. So phosphite is PO3 with -3 charge. H, the -3 goes there. Review those, okay? If it had been phosphate, right, it would have been phosphoric acid. I ate too much and now I feel icky. So review your acid naming, right? So actually, there's that, because there's PO4. So phosphate, I ate too much, ATE, and now I feel icky. All right, guys, phosphoric acid. So those are the acid naming. You really want to know those. There's several in your test. All right, and again, this is already up on Canvas for you to print out if you want to print this along. London dispersion forces. These happen if it is a non-polar covalent. So it has no lone pairs. It is symmetrical. The bond is a non-polar bond. That's London dispersion forces are at work. If you have a dipole-dipole force, then you're polar covalent. So you're looking for the polar bonds, which are going to have asymmetry or lone pairs or unlike things bonded to your center atom. Dipole-dipole will be your strongest in that case, except where if it's polar, but there's also hydrogen involved. Okay, so this is the really strong one. It's the strongest of all. You see this anytime if there's hydrogens involved, probably you're looking for your hydrogen bond. Okay, so things like H2O have hydrogen bonds as their strongest. From weakest to strongest, London is weakest, dipole-dipole is in the middle, hydrogen is the strongest. Okay, so make sure we understand the forces here. London dispersion forces are not going to be the strongest ones at work if you're dealing with polar. You want to make sure you're clear on the differences between these two. Okay, ionic bonds. Let's see. I'm looking for their particles are called this one. Ionic bonds forms between a metal and a nonmetal. And this type of bond, electrons are transferred. Their particles are called formula units. Unlike a covalent bond where electrons are shared, sharing is caring. If you are covalent, sharing is caring. Their particles are called molecules. Okay, so review quick of the naming. We did a little bit of that already, but let's see if we want to do our naming. So this is an ionic bond. I know this is an ionic bond because magnesium is a metal. Magnesium is in group 2, so I do not need a Roman numeral. So this is magnesium chloride. Unlike iron, which is a metal, so that would get a Roman numeral. Where does the Roman numeral come from? If you're looking on the periodic table, the Roman numeral will come from if there is nothing there, right? And this one, there's nothing else, there's nothing there. It doesn't mean that they don't have an oxidation number, it just means that their oxidation numbers must be the same. You know the oxidation number of oxygen, right? It's -2. So this must be iron 2 oxide. All right. Review your periodic trends. I encourage you to do that. So let's see. Review your shapes. Hopefully we can all bonds. We can write these down. Think about the special exceptions like boron, boron the moron, right? So boron doesn't need a full octet. And that's why it is trigonal planar and not pyramidal. That's a big difference because that will affect the molecule polarity. Okay, this is trigonal planar. The bond type is nonpolar because the boron is sharing equally. It does not have a lone pair. Okay, let's compare that to something like NH3, which if you don't remember, NH3 does have a lone pair. And that is because nitrogen does not, it needs a full octet unlike boron. Okay, and it can bond nicely and with 3 hydrogen, but it's not full. There are still some electrons there that are by themselves that it was not able to bond out together. So this lone pair changes the polarity. Now we have a molecule that is polar because lone pairs cause polarity, and that also kind of picks it up and makes these bonds kind of come at an angle. So this is actually trigonal pyramidal. Okay. Now, if we are trying to figure out our bond type, that's where we're going to use our electronegativity chart. And we'll give you these values, but you're just going to kind of see where they fall within the ranges. Okay. So I've got nitrogen, hydrogen. Nitrogen is 3, hydrogen is 2.1, and you want to subtract. Okay, so 3 minus 2.1. Okay, and then we'll give you those ranges, right? So you're not going to have that memorized. We will give you the ranges and how that would fall out. So there's a little instruction. Alright, so I'm going to end this here, but I'll post more later if I can, because we've got some little kids here too late. Okay, future Miss Sapphire back. Alright, we're going to draw a couple more. P2, our shape. I know this is going to be linear because there's only 2 things involved. Because they're the exact same thing, they're going to share equally, right? Neither phosphorus is going to take more from the other, so it's going to be nonpolar as a molecule. The difference is going to be 0, so it's also going to be nonpolar covalent. I know the electronegativity difference is going to be 0 because it's just phosphorus minus phosphorus on the electronegativity chart, right? So the phosphorus, 2.1 minus 2.1. My Lewis structure, I wanted to draw this one in particular because I saw several of y'all making some mistakes with nitrogen, which has this very similar structure, obviously, to phosphorus because they have the same number of valence electrons. Okay, so, oh, and I almost started drawing nitrogen. We'll make this a weird-looking P. It's a P now. It's a P. So, phosphorus and phosphorus. Think about how they would bond. So, how many valence electrons does phosphorus have? Has 5. So, I'm going to draw them in. 1 and 2 always go together. Then 3, 4, 5. 3, 4, 5. So, a lot of you, I noticed, were just making a single bond when you had it with nitrogen. These are, when they're bonding together, 2 phosphorus or 2 nitrogens, they're always going to make a nice triple bond because electrons don't like it when they're alone. So if there are other bonds around or other single electrons, they're going to share them. These are really strong bonds. A triple bond is really strong. So I wanted to point that one out. Okay, let's do another one. I'm going to go ahead and do this one right here only because it's long and it's a more complicated structure. So my shape, I can count how many things are going to be bonded here. I've got 2, 3, 4. Okay, I know this is going to be tetrahedral just because I can count the number of atoms here. It's got to be tetrahedral because there's 5 atoms. Now, a lot of the times students get confused about what to put in the middle. Think about how the valence electrons, what their requirements are to meet an octet. So for me, I think automatically, okay, carbon, first of all, is almost always at the center of tetrahedral molecules, carbon or silicon, and that is due to the number of valence electrons they need in order to complete their octet. So carbon's going to be in the center because it's the only one that wants 4 things bonded to it. Okay, so here we go. Then you can just start placing. So I'm going to put my chlorines. I'm drawing all their electrons. Then I'm going to put my fluorine. And then I'm going to put my hydrogen. So there's my Lewis structure. This, as a molecule, is going to be polar because the fluorines and the chlorines are not going to share equally with that hydrogen. Okay? It's not going to be an equal sharing. So polar, I think of polar bears. Is a polar bear going to share with you? Maybe, but probably not equally. The polar bear is bigger than you, so he'll probably take a greater amount of his share. So for our bond types, we have a lot of different bonds going on, so we have to actually calculate them out for CH, Cl, and Cf. So I'll do CH first. CH, our electronegativity values, we've got C at 2.5, we've got H at 2.1, so that is a difference of 0.4. And that means it is going to be polar covalent. So I just made myself a little chart there. These are our values that we want you to use. These will vary from textbook to textbook and from different sources, but these are the values we want you to use. This could also be ionic or very polar in that range, just to point that out. So I can see that this is just very slightly, the bond between C and H, very slightly polar because it's 0.4. So this one's polar. So now let's look at the bond between C and Cl. We'll look at our difference in electronegativity values. Whoop. So C is again 2.5, Cl is 3, so if I subtract, my absolute value is 0.5. Again, that is slightly polar, so that's 0.5 and it's polar. And now I'm going to do C and F. So F is 4, Ooh, F's 4. Okay, so that's a strong one, right? That's not going to be sharing equally. F is 4, and C is, once again, 2.5. So when we subtract, okay, you're going to get 4 minus 2.5, and you're going to get 1.5. So our difference is 1.5. So that is a much stronger polar covalent, but it's not considered extremely polar or ionic. It's just on the upper end of polar covalent. So each individual bond is also polar. All right. So now I think that is really actually going to do it for this video, because I do want you to practice drawing some of these on your own. But if you have any questions, make sure you ask. You may be wondering about this very last page, and I'm going to say we actually cut this due to COVID. Don't worry about this last page, okay? So don't worry about this last page. Really focus in on your ionic covalent naming and formula writing. That's the big part of this test. Understanding the IMFs, okay? And of course your Lewis structures. And that's going to be it. Don't worry about that last page.